the previous lecture we were discussing about the basics of what is boundary layer, what is boundary layer theory and the boundary layer equations. Today what we will do is we will consider the boundary layer equations for flow over a flat plate and see that how we can solve this equation. So, there is a numerical way of solving this equation and that is done after a suitable transformation known as similarity transformation. So, what is similarity transformation and how does it originate from the physics of the problem? We will try to get into that first. So, imagine that there is a flat plate like this and there is a boundary layer the edge of which is like this. Now, if you plot the velocity profiles u versus x, you will see that the velocity profiles are different at different x. The simple reason is that the boundary layer is as if it is getting stretched from this delta, it is getting to this delta. So, this velocity profile is sort of getting stretched, right. You can imagine that there is a string here, this string when stretched becomes this one. So, now this is u versus y and it is different for different values of x, but if you make a plot of u by u infinity versus y by delta, then this is normalized between 0 to 1 and this is normalized between 0 to 1. So, the entire result is within a box of dimension 1 and you will see that interestingly all results, that is the velocity profile here, the velocity profile here, all converge to the single velocity profile. Where is the x dependence gone? The velocity profile is clearly dependent on x. So, where is that x dependence gone? The x dependence is here, this delta is a function of x. So, now if you define a variable eta is equal to y into gx, where this gx will scale with 1 by delta, and if we are able to transform the partial differential equations which describe the boundary layer in terms of a ordinary differential equation expressed with this as an independent variable, then we can say that this problem is self similar. That means similarity transformation exists. So, with this understanding, let us say that we define u by u infinity is a function of eta where eta is y into a function of x. So, the boundary layer equations assuming 2 dimensional incompressible flow and steady flow So, now we will write various terms based on this assumption that u by u infinity is a single valued function of eta, where eta is essentially a variable that scales with y by delta. So, this u is u infinity into f. What is this? This is u infinity df d eta into del eta del x is y into g dash x, right. Similarly, what is this? This is u infinity df d eta into del eta del y is g. So, if you want to evaluate this, this is a second order derivative of this one. So, u infinity g x into del eta del y is another g x, that will make it g square. So, the strategy what we will follow is something like this. We will eliminate v from these two equations, because the velocity profile u by u infinity is expressed as the function, v is not included in this representation. Because v is not included in this representation, we will eliminate v. So, let us write what is v from here. So, maybe let us write it here. So, v is this is nu u infinity d2f d eta 2 into g square minus u infinity square f df d eta y g dash right divided by u infinity df d eta into g, right. So, this is nu d2f d eta 2 by g df d eta minus u infinity f y g dash by g. So, what we will do is we will differentiate this with respect to y and equate that with minus del u del x to eliminate v. So, if you differentiate this with respect to y, into del eta del y, that is g, right. So, this g and this g gets cancelled, right. Then minus u infinity f the derivative with respect to y, if you write, then what, there will be two terms, because this is a function of y and this is also a function of y. So, u infinity g dash by g, let us write, then df d eta into g minus into y plus f, right. So, this becomes nu d d eta of minus u infinity df d eta y g dash minus u infinity f g dash by g, right. Now, this is equal to minus del u del x. So, this is equal to minus u infinity df d eta y g dash. Okay. So, then this term and this term gets cancelled, and then you are left with nu d d eta minus u infinity f g dash by g is equal to 0. Maybe one g extra g has been missed somewhere. Let us see this. So, this is u infinity, we will let us see anyway. So, let us check the calculation once. This is u infinity f, this is all right. So, del v del y. So, v is nu u infinity del 2 u del y 2. So, nu d 2, so u infinity g square d 2 f d eta 2 minus u infinity square f d f d eta into y g dash by u infinity f. So, nu d 2 f d eta 2, yes, there is a g square here that was missing, right. There is a g square. So, this is what I found it is missing. So, nu d 2 f d eta 2 by into this g square was missing here, right, g square by g d f d eta. So, let us write nothing very different, only the g square will be there in the numerator, right, one additional g square. So, nu g square, right. I think that was the only thing that was missing, right. So, then let us erase this, hopefully the remaining algebra is correct. So, you can write d d eta of d 2 f d eta 2 by d f d eta into 1 by f is equal to u infinity by nu g to the power minus 3 dg dx, right. So, this g to square and this g will make it g to the power minus 3 and dg dx, this g dash. So, then this is a function of eta only and this is a function of x only, right. So, a function of eta only is equal to a function of x only if each is a constant, right. This implies this is equal to c. So, g to the power minus 3 dg is equal to c nu dx by u infinity. So, if you integrate it, then it will become g to the power minus 2 by minus 2 is equal to c nu x by u infinity plus some constant c1. Now, what is g? That is the very important physical question. So, g scales with 1 by delta. So, at x tends to 0, that is at the edge of the boundary layer. Remember, at the edge of the boundary layer where x is exactly equal to 0, delta is not defined, it is a singular point. So, at x tends to 0 plus, you have delta tends to 0, that means g tends to infinity. So, if g tends to infinity, this is 0. So, let us write this at x tends to 0 plus g tends to infinity, that means C1 equal to 0. So, that means you can write 1 by g square is equal to minus 2 c nu x by u infinity. So, g is equal to square root of u infinity by minus 2 c nu x, right. So, from here what can you conclude about the value of c? C can be anything, but it has to be negative, because this g is physically scaling with 1 by delta, that means it has to be a positive term. So, c must be negative. So, if c is negative, we could choose c, a good number, maybe c is equal to minus half or minus 2, like that. So, let c is equal to minus half, this is not a must, but you can choose this. So, if you choose that, then g is equal to u infinity by square root of nu x. So, because this is scaling with 1 by delta, you can say that delta is proportional to square root of x. So, this is how the boundary layer thickness grows with x, given that the other parameters remain the same. So, now our main objective is not just this, main objective remains to determine the velocity profile, and that comes from this equation. So, 1 by f d d eta Okay. So, now if you integrate this, an integro differential type of equation is obtained, right. To make it completely differential equation, you can define this as a new variable f. In other words, small f is equal to df d eta. Remember, this f physically is velocity and this is the cross gradient of some function f. So, capital F is physically like the stream function. Recall, the physical meaning can be established by noting that u is equal to del psi del y, that is the definition of stream function for 2 dimensional incompressible flow. So, try to establish an analogy of this with this one, right. U is represented by f and psi is represented by capital F. So, this see, this is a very important aspect of teaching this part. This is purely a mathematical derivation that you have to go through, but never lose the physical meaning of various parameters that you are going to introduce through this equation. So, with this, now you can write, so this will become f triple dash plus half f, this will become capital F double dash is equal to a constant k, right. Question is, what is the value of this constant? So, to understand that value, you have to keep in mind that this is nothing but stream function physically. This is nothing but what is this? This is the first derivative of velocity, right, and this is the second derivative of velocity physically, right. Now, to get this boundary value of k, this physical relationship between capital F and the physical variables need to be clearly kept in mind. So, recall that at the, so you have the boundary layer equation, okay. So, at the wall you can apply this equation at the wall. So, at the wall u wall, this is 0, no slip, V wall equal to 0, no penetration. This means that this is equal to 0 at wall, right. If this is equal to 0 at wall, that means this is also 0 at wall, 0 at eta equal to 0, which is the wall. The stream function, what is its value at the wall? Remember that the wall is itself a streamline, because by definition there cannot be any flow across the streamline. So, by definition the wall is like a streamline, because you cannot have any such flow until and unless there are holes in the wall. So, when you do not have this, then the consequence is as follows, that the wall itself represents a psi equal to constant line, which is a streamline. So, the psi equal to constant can be chosen as anything. So, for our benefit to set this constant to our liking, we choose that f is equal to 0 at eta equal to 0. We could choose anything instead of 0, 1, 2, but whatever we had chosen, then this k would be dependent on this at the wall, that we do not know. So, to fix it up, the best is to set it 0, so that the value of this at the wall does not matter, and then this means that k is equal to 0. So, you are left with f triple dash plus half f double dash is equal to 0. This is the famous Blasius equation. What are the boundary conditions? This is a nonlinear third order ordinary differential equation. So, it will have 3 boundary conditions. What are these? At eta is equal to 0, you will have the stream function equal to 0. At eta is equal to 0, small f, that is the velocity, is equal to 0, that means df d eta is equal to 0, and at eta tends to infinity, u by u infinity is 1, that means small f is equal to 1 or df d eta is equal to 1. Okay. So, with these 3 conditions you can numerically solve this using various techniques such as shooting method, for example. We have a separate tutorial for you where it will be illustrated how to numerically solve this equation. So, I am not getting into that in this main lecture. So, this will give you a solution for f. So, then if you make a plot of the velocity profile as a function of eta, then from the solution of this the numerical result will come to be something like this. So, u by u infinity will tend to 1 when this is roughly equal to 5. This is the Blasius solution. So, then let us write the solution here. So, eta is equal to y g x. So, at eta is equal to 5 roughly y is equal to delta, that is the main result of this. So, 5 is equal to delta g x. G x is, what is g x? Square root of u infinity by nu x. So, you can write delta by x is equal to 5 into square root of nu x by u infinity x square. This by x will bring it x square. This is nothing but 5 into Reynolds number to the power minus half, where Reynolds number is u infinity x by nu. This is local Reynolds number. See the power of the order of magnitude analysis. The order of magnitude analysis, just by one line of equating the order between the inertia force and the viscous force at the edge of the boundary layer, came with this scaling, that is delta by x is of the order of Reynolds number to the power minus half. This solution, Blasius solution, is only giving the constant that should come out of it. I will take just a couple of minutes more to define 2 parameters. One is skin friction coefficient. So, this is the non dimensional wall shear stress. So, this is tau wall by half rho u infinity square. What is tau wall? Tau wall is mu so this is mu u infinity df d eta into del eta del y is g, right, because we have to get the solution in terms of our variable that we have solved by half rho u infinity square. So, u infinity and u infinity will be cancelled. So, df d eta at the wall, that is at eta equal to 0, this is nothing but f double dash at 0. This will come out to be 0.332 if you numerically calculate this is 0.332 numerically if you calculate this. So, then if you substitute this g, this Cf, this 0.332 divided by this half will make it 0.664 into Reynolds number to the power minus half. And finally, we will calculate something called as drag coefficient. So, drag coefficient, so for that let us draw the picture of the plate. So, at a distance x, if you take an element dx and let us say b is the width of the plate, then on this strip what is the drag force? Tau wall into b into dx, right. So, the total drag force this is the L is the length of the plate. The drag coefficient CD is this FD into B into L. See, this is a general definition of the drag coefficient, drag force divided by half rho V reference square divided by a reference area. The reference area is the area which is physically meaningful to giving rise to the drag force. Here the surface area of the plate is physically meaningful to give rise to the drag force. So, this you can write tau wall So, this will be this b gets cancelled, then mu, this is d small f d eta means f double dash 0 again into del eta del y is gx, gx is square root of u infinity by nu x, right, into dx, integral of this 0 to L by half rho u infinity square L. So, this will be x to the power minus half dx. So, this will be x to the power minus half plus 1 divided by minus half plus 1. So, another half will come. So, with this half will come another half. So, this will be this half into half, when this goes to the numerator it will be 4 into f double dash 0 into this will now become Reynolds number to the power minus half, where Reynolds number is based on L, because this L x when the definite integral will be put it will become L. So, this will be 4 into 0.332, that is 1.328. So, always whatever is this, Cf will be double of that and Cd will be 4 times that, and the scaling is here, it is Reynolds number with respect to the length scale L, and here it is local. So, this is Reynolds number with respect to the local length scale x. Thank you very much. We will continue in the next lecture.